Welcome to Miss Perry's online physics lectures. Today's lecture will be about motion diagrams. A motion diagram is a picture representation of the motion of an object, kind of like a movie. So if we were to draw a motion diagram for a car traveling at a constant velocity, here's what it would look like. Here's our car traveling along at a constant velocity. If I were to take a picture each second of that car's location, if it's going along at a constant velocity, then each second or each time I take that picture, notice how the car is spaced evenly apart. You could also picture it if you were traveling in a car and that car's going a constant speed. Let's say that car has an oil leak, and every second a drop of oil hits the pavement. Your motion diagram would represent that dot each second. So it's a representation of what your object is doing at equal intervals of time. And we represent the velocity in our motion diagram with an arrow. Since that arrow is a vector and velocity is a vector. And notice how the arrows are all pointing in the direction that the object's moving, and they're all the same size because our car is traveling at a constant velocity. So the magnitude of our velocity vector, the size of our arrow, stays constant throughout the object's motion. So here's a more specific example. Draw a motion diagram for a car traveling at a constant velocity of 3 meters per second for a time of 4 seconds. Include velocity vectors. Here's our car traveling along, and we take a snapshot of that car in 1 second intervals. 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds. Notice this is a time period, a time span of 4 seconds. But notice that we have 5 dots representing our car. You will always have one more dot than you do seconds, because you always start your motion diagram at 0 seconds. Now, if I was to draw my velocity vectors into my motion diagram, I would include with it the magnitude of that velocity vector. So write in next to your arrow 3 meters per second. And for each of the next 4 velocity vectors, we're still going 3 meters per second. So notice, the two things that you have to include with your motion diagram are the times, t equals 0 seconds, t equals 1 second, all the way up to 4 seconds, and also your velocity vectors labeled. You don't necessarily have to draw the cars along with it. The dot representation is perfectly fine. I don't expect artists. I just expect you to draw the physics correctly. And if the question asks, you can also figure out your displacement from your motion diagram. At 0 seconds, our displacement x in this case would be 0 meters. But at a time of 1 second, we have traveled 3 meters. The way you can figure that out is to use your average velocity formula. Average velocity equals displacement over time. Your average velocity is 3 meters per second over a time interval of 1 second, which would give you a displacement at 1 second of 3 meters. And you can continue this process all the way up to 12 meters at 4 seconds. Motion diagrams can also represent objects that are accelerating. One version would be accelerating by speeding up. So you would have an object that's getting faster and faster and faster. And notice, since the velocity is increasing, your velocity vectors represented with arrows should be getting bigger in size as your speed increases. It can also represent acceleration by slowing down. If your object is slowing down, that means that your dots would be getting more closely spaced together because your velocity vectors are getting smaller and smaller and smaller. As you're slowing down, you're covering less distance per second, which is why your dots are getting closer together. Let's try one last motion diagram. Draw a diagram for a car starting from rest and accelerating at 4 meters per second squared for 4 seconds. For this motion diagram, we always start at 0 seconds. And since it says our car is starting from rest, our initial velocity would be 0 meters per second. When we talk about acceleration, acceleration is the rate of change of your velocity. So it's how much your velocity changes each second. So another way you can think about 4 meters per second squared, it changes by 4 meters per second per second. So every second your velocity will change by 4 meters per second. So by 1 second, your velocity will have increased by 4 meters per second. By 2 seconds, your velocity again will have increased from 1 second by another 4 meters per second. So 4 meters per second plus 4 meters per second would give you 8 meters per second. At 3 seconds, 12 meters per second. And by 4 seconds, you've reached a speed of 16 meters per second. And again, notice how my dots are getting farther spaced apart, and the arrows are increasing in length. Now, can we use this information to determine how far the car has traveled after 4 seconds? You can still use the process of average velocity equals displacement over time. If I were to look between 0 seconds and 1 second, I'm going from 0 meters per second to 4 meters per second. So my average velocity over that period of time would be 2 meters per second, excuse me. So my average velocity is 2 meters per second, and this occurs over a time span of 1 second. So when I plug those values into my equation, average velocity equals displacement over time, I would find that in that first second, I've traveled a distance of 2 meters. And if you continue that process all the way up to 4 seconds, you can find that you would travel a total distance of 32 meters, or a total displacement, in this case, of 32 meters right or east, however you want to determine the direction. If you have any questions, comments, or concerns, please feel free to talk to me during class or after school.